Introduction. Students, what is this? Radius of a circle. Students, what is this? Diameter of the circle? Yes, you're right. And what if I mark a line segment here? What is this now? It's a chord. Correct. And what do we call this line? Tangent. Yes, this is a tangent of the circle. Today we will study about circles and tangents. Objectives. At the end of this lesson, you'll be able to define tangent of a circle, prove the theorems related to the tangent at any point of a circle, prove that the lengths of tangents drawn from an external point to a circle are equal, solve examples related to the tangent of a circle. Definition. Students, let us draw a circle and a line in a plane. We can see that the line and the circle do not have any common point. So, the line is called a non-intersecting line with respect to the circle. This is the other way we can draw a line and a circle. We can see that there are two common points, A and B, that the line and the circle have. In this case, the line is called a secant of the circle. And this is the third way we can draw a line and a circle. We can see that there is only one point A which is common to the line PQ and the circle. In this case, the line is called a tangent to the circle. So, a tangent to a circle is a line that intersects the circle at only one point. Activity. To understand more about tangent, let's do an activity. Draw a circle and a secant AB of the circle. Now on both sides of this secant, draw various lines parallel to it. We will find that after some steps, the length of the chord cut by the lines will gradually decrease, and it becomes 0 on both the sides of the secant. Now look at the positions AB and AB of the secant. These are the tangents to the circle parallel to the given secant AB. We can also observe that there cannot be more than two tangents parallel to a given secant. The common point of the tangent and the circle is called the point of contact, and the tangent is said to touch the circle at the common point. Theorem. The tangent at any point of a circle is perpendicular to the radius through the point of contact. We are given a circle with center O and a tangent xy to the circle at a point P. We need to prove that OP is perpendicular to xy. Take a point Q on xy other than P and join OQ. Also, the point Q must lie outside the circle, because if Q lies inside the circle, then xy will become a secant and not a tangent to the circle. Therefore, OQ is longer than the radius of OP of the circle. That is, OQ is greater than OP. Since this happens for every point on the line xy except the point P, so we can say that OP is the shortest of all the distances of the point O to the points xy. Hence, OP is perpendicular to xy. Remarks. From this theorem, we can also conclude that at any point on a circle, there can be one and only one tangent. And the line containing the radius through the point of contact is also sometimes called the normal to the circle at the point. Number of tangents from a point on a circle. Can you guess how many tangents from a point of a circle can be drawn? Let's perform an activity to check this out. Draw a circle on your notebook. Now take a point P inside it. Draw lines through this point. We will find that all the lines through this point intersect the circle in 2 points. That means it is not possible to draw any tangent to a circle through a point inside it. The other case is to take a point P on the circle and draw tangents through this point. We can observe that there is only one tangent to the circle at such a point. Finally, take a point P outside the circle and try to draw tangents to the circle from this point. We can find that exactly 2 tangents to the circle can be drawn through this point. The length of the segment of the tangent from the external point and the point of contact with the circle is called the length of the tangent from the point to the circle. Here PT1 and PT2 are the lengths of the tangents from P to the circle. The lengths PT1 and PT2 have a common property which we will learn in the next screen. Theorem. The lengths of tangents drawn from an external point to a circle are equal. We are given a circle with center O, a point P lying outside the circle, and 2 tangents PQ, PR on the circle from P. We need to prove that PQ is equal to PR. Let's join OP, OQ, and OR. Now we know that the angles between the radii and tangents are right angles. Therefore, angle OQP and angle ORP are right angles. Now in right triangles OQP and ORP, OQ is equal to OR because these are the radii of the same circle. OP is equal to OP, common. Therefore, by RHS congruence rule, triangle OQP is congruent to triangle ORP. This gives PQ is equal to PR because congruent parts of a congruent triangle are always congruent. Example. Now look at this figure. We can see that AB is a tangent to the circle with center C. AB is 15, AC is 17, and BC is x. We have to find the value of x. We can see that x is a radius of the circle. Since x contains B and AB is a tangent segment, therefore by using the theorem of tangents, we can say that x is perpendicular to AB. So the triangle formed by x, AB and CA is a right triangle. Now by using the Pythagoras theorem we get 15 square plus x square is equal to 17 square, or x square is equal to 64, which gives us x as 8. Example. 2 tangents TP and TQ are drawn to a circle with center O from an external point T. Prove that angle PTQ is equal to 2 angle OPQ. We are given a circle with center O, an external point T and 2 tangents TP and TQ to the circle where P and Q are the points of contact. We need to prove that angle PTQ is equal to 2 angle OPQ. Let angle PTQ is equal to theta. Now from the theorem of tangents we know that the lengths of tangents drawn from an external point to a circle are equal. Therefore, TP is equal to TQ. So, TPQ is an isosceles triangle. Therefore, angle TPQ is equal to angle TQP, which equals 1 upon 2 into 180 degree minus theta, which is equal to 90 degree minus 1 upon 2 theta. Also, we know that tangent at any point of a circle is perpendicular to the radius through the point of contact. Therefore, angle OPT is equal to 90 degree. So, angle OPQ is equal to angle OPT minus angle TPQ, which equals 90 degree minus 90 degree minus 1 upon 2 theta, equal to 1 upon 2 theta equal to 1 upon 2 angle PTQ, or angle PTQ is equal to 2 angle OPQ. Example. Look at the figure given. Find the value of x. In triangle OPT, angle OPT is 90 degree because OP is perpendicular to TP. Also, by using angle sum property of a triangle, we can say that x degree plus 56 degree plus 90 degree is equal to 180 degree, which is equal to x plus 146 degree, which equals 180 degree. Solving this, we get x as 34 degree. Hence, the value of x is 34 degree. Did you know? The word tangent comes from the Latin word tangere, which means to touch, and was introduced by the Danish mathematician Thomas Finnecke in 1583. Summary. Let us summarize what we have learned. A tangent to a circle is a line that intersects the circle at only one point. The tangent to a circle is perpendicular to the radius through the point of contact. The length of the two tangents from an external point to a circle are equal.